In this video, we're going to take a closer look at the resistance that a wire provides in an electric circuit. When we typically solve circuit problems, we assume that we have ideal wires, meaning that we assume there's no resistance in a wire, and so that if we have a power supply and something that provides resistance like this light bulb, we make the assumption that there's no potential difference dropped, there's no voltage drop across the wires, because we're assuming there's zero resistance. When in reality, we know that wires provide some resistance, it's typically negligible. So the question is, what is it about a wire that provides a little resistance or a lot of resistance? What is it about a wire that affects how resistive it is to current flow when there's a potential difference across it? In this simple circuit, with a potential difference of 3 volts across our entire circuit from the red wire to the black wire, across our light bulb, we can see that there's a 2.98 volt potential difference drop across there. There's only 0.02 of a volt that drops across both the red wire and the black wire combined. Most of it drops across the light bulb. But what if we were to take this light bulb out of our circuit and we just had a single wire, and if we connected one single wire from the positive to the negative terminal of our power supply, if we had a 3 volt potential difference across there, there wouldn't be 100th or 200ths of a volt that drops across there. We'd have the full 3 volt potential difference drop across that entire wire. So I want to go through just a little bit of investigation and thinking to try to think about what is it about this wire that provides resistance, and what could we change about a wire which might change its resistance. Okay? Well, if you think about it, a wire is just inside of there, it's a cylindrical piece of metal. And we could change a couple different things about the dimensions of the wire. If we had 2 wires in series, we're effectively increasing the length of that conductor. Or if we take 2 wires and put them in parallel and apply a potential difference across one side to the other side, with wires in parallel, we're effectively increasing the surface area of that wire, the cross-sectional area of that wire, to allow current to flow through it. So we're going to do a few little investigations to find out how does changing the length of a wire affect its resistance, and how does changing its cross-sectional area affect its resistance. So the first thing we need to do is figure out the resistance of a single wire, and to do that we're going to use Ohm's law. The current through something is equal to the change in potential across that thing divided by the resistance of that thing. And we can use that equation to solve for R as long as we know the change in voltage across, and we can measure the current through it. And our power supply will allow us to do that. We can put a known source of potential difference across there, our wire, hook one side to the red side, the other side to the black side, and this power supply will also allow us to measure the current which actually travels through the wire. So right now there's a 0 volt potential difference across both sides of our wire, and I'm going to increase the voltage across there to about 0.15 volts. Here we go. So there's 0.15 volt difference between what's connected to the positive side and the negative side, the red to the black, across this wire. And there's current going through it, conventional current going from the positive side to the negative side. And if I flip this switch right here, it'll tell us how much current is going through that wire. So we can see that there's about 1.97 amps of current flowing through this wire when there's a potential difference of about 0.15 volts across it. So we can calculate the resistance of that single wire by taking 0.15 volts divided by 1.97 amps, and that gives us a resistance of about 0.076 ohms, a little bit under 1/10 of an ohm. Well, let's find out if we lengthen this wire, how does that change the resistance? Or if we thicken that wire, we have more cross-sectional area by having 2 wires in parallel, how does that affect the resistance of the overall wire? So let's first start by lengthening that wire. So I'm just going to take an additional section of wire that's the same length of the original one and hook these 2 things together. So now I'm going to have a wire that's twice as long, and let's find out what is the resistance of something that's twice as long with the same cross-sectional area. So I'm going to hook it again from the positive to the negative side and make sure there's about 0.15 volts potential difference from one side to the other side. So now we have current again flowing through our longer wire, and let's find out how much current actually goes through there. So if I flip the switch, we can see now that there's only 0.98 amps of current. So it's about half the amount of current which is traveling through there. And if we have the same potential difference and our current is now half the size, what does that suggest is true about the resistance? Well, that suggests if we have the same potential difference and we have half the current, that means our resistance is about double. We've got twice the resistance. So when we doubled the length, that increased the resistance of the wire itself by about 2 times. So that suggests that length is proportional to resistance, or the resistance of a wire is proportional to length. If we double the length, we double the resistance, and the current which traveled through there shows that that's the case. Well, what happens if we, instead of changing the length, we change the cross-sectional area? So I'm going to go back to our first single wire, where we've got about 2 amps of current flowing through there, right, with a potential difference of 0.15 volts across there. Now, I'm going to keep the length the same, but I want to effectively double the cross-sectional area of the conductive pathway from the high potential side to the low potential side. And the way that we're going to do that is we're just like with our cylinders here, right? Instead of increasing the length, we're going to kind of put them side by side. So we've got twice the cross-sectional area, so we've got essentially 2 wires in parallel. So if I take the second wire and hook one side of the positive side, one side of the negative side, just like our first wire, we're going to have 2 wires going from the positive side to the negative side, both the same length, you can see. And effectively, when they're in parallel like that, we've doubled the cross-sectional area. So let's go ahead and look at our current. Well, our potential difference, again, is still 0.15 volts across each side. And if I flip the switch, we can see there's about 3.8 amps of current. That's almost 4 amps of current. That's double what it was originally. Because remember, with the first wire, if I take one of these things off, there's about 2 amps of current which goes through there. And when I add the second wire, instead of 2 amps total, there's now about 4 amps total of current going through there. So for the same potential difference across our effective wire, our thicker wire, we now have twice the current, which means our resistance has to be half of what it was originally. So what effect does increasing the surface area add? When we had 1 wire of a given length, we had 2 amps. When we had 2 wires kind of side by side in parallel, when we doubled the area, the current was doubled, which means the effective resistance of these 2 things together was half the original resistance. That suggests an inverse relationship between the cross-sectional area of a wire and the resistance of that wire. So it turns out that the resistance of any material is based on its length and its cross-sectional area, and it also depends on the type of material. If you think about it, if you take a length divided by an area, a length in meters divided by an area in square meters, that's not going to give you a value of resistance. There has to be a proportionality constant. So resistance is proportional to length and inversely proportional to area, but in order to turn that into an equation, we need a proportionality constant. And that proportionality constant depends upon the material in question. That proportionality constant is called the resistivity, and it's based on the material involved. In order to calculate the resistance of a piece of material, you need to take that proportionality constant times length divided by area. And here are some resistivity values for different materials. For copper wire, it's 1.7 times 10 to the negative 8 ohm meters. And those units just make sure that the units work out to be ohms when you're calculating your resistance. As we go down in this table, the resistivity increases. So a higher resistivity will a higher resistance for the same length and cross-sectional area. Aluminum is a little bit more resistive for the same amount of material as copper. Seawater is even significantly more. It's got a resistivity of 0.22 rather than something like 20 millionths of an ohm meter. When we get to drinking water, it's got an even higher resistivity, and something like hard rubber, which is an insulator, has an incredibly high resistivity. So now we know how to calculate the resistance for any given piece of material as long as we know that proportionality constant, which is called the resistivity, length, and the cross-sectional area.